Welcome to the course on Introduction to Electrical Engineering. We will have a lecture 34 today on direct current machines part 2. So, we would like to of course, have outline of the today presentation starting from speed control of DC motor, then we will talk about torque of DC motors, then speed torque characteristic of different DC motors followed by speed control of other DC motors, and then we will have a exercise, then the numerical solved problems. So, coming to now speed of a DC motor, which we defined last time we discussed the relation of induced EMF in the armature winding. So, that was E equal to 2 into Z by C into NRP upon 60 into phi volt like. So, well, for a given machine Z, C and P are fixed. In such case we can write E equal to K N R into phi, and where K is 2 Z upon C, P upon 60, because all these parameters are constant for a already a machine available or motor DC motor available with you. So, you can call it is directly proportional to speed and flux like. Induced EMF is directly proportional to speed and flux like. So, the speed of this DC motor is approximately proportional to the voltage applied to the armature and inversely proportional to the flux, and all the methods of controlling the speed involve the use of either both of these relationships. So, we can say substituting the value of E in the expression of volt ampere equation. So, V is equal to K, that is E plus IARA, or you can call it V equal to K NR phi plus IARA, and from this we can have NR equal to V minus IARA divided by K phi, where V the applied voltage, IA the armature current, RA is the resistance of armature, and phi the flux of course set up by the field winding or maybe by permanent. So, this is the speed in, you can call it, of the shaft of this DC motor like. So, the value of IARA usually less than 5% of the terminal voltage. So, that we can say NR is proportional to V upon phi. So, now we can define of course, the torque in a DC motor. So, if we start with the equation V equal to E plus IARA, then we can say and multiply each term by IA, namely the total armature current. We have now V into IA equal to E IA plus I square RA. So, V IA represents the total electrical power supplied to the armature, and I square RA represents the loss due to the resistance of armature circuit or armature winding. So, the difference between these two quantities, namely E into IA, therefore, represents the mechanical power developed by the armature of the DC machine or by the DC machine. So, all this mechanical power is not available externally, since some of it is absorbed as friction and windage loss at the bearing and at the brushes, and some is wasted in hysteresis slot and in the circulating eddy current in the ferromagnetic core. So, if M is the torque in Newton meter exerted on the armature to develop the mechanical power just referred to, and if NR is the speed in revolution per minute, then the mechanical power developed, you can define that is 2 pi m n r upon 60, because NR is in RPM. So, we have to divide 60 to convert into RPS, and that we by multiplying 2 pi it becomes radian per second, multiplied the torque, that goes into watt. Hence, we can say 2 pi m n r upon 60 equal to EAIA or equal to 2 upon Z upon C NRP upon 60 into phi into IA. So, from this we can have M equal to 0.318 I upon C into Z P phi in Newton meter, and for a given machine Z C P are already fixed, we talked about earlier, in which case M is proportional to IA into phi. So, the torque for a given DC motor is proportional to the product of armature current and the flux per pole. Now, coming to speed characteristic of the DC motors. So, we have now typically with few exceptions, DC motors are generally shunt type motor, where the first case the field winding is connected in parallel to the armature series, when the field winding is connected in series with the armature, and or the compound where you have a shunt field and as well as the series field. It can be long shunt or short shunt. If typically you can call it, if shunt field winding is connected across armature, we call it like a short field kind of compounding machine, or if it is connected like a after series with the armature, then it is called long shunt. So, the speed characteristic of a DC motor usually represents the variation of speed with the input current or input power, or its shape can be easily derived from expression. So, you have here the different shapes like A, then C and B, and these characteristic are for really for different motors. So, here N R equal to we already explained V minus I R upon K phi. So, in shunt motors the phi is only slightly affected by the armature current, and the value of IARA at full load rarely exceed hardly 5% of the voltage. So, that the variation of speed with input current may presented by curve A in the figure is almost like a flat characteristic. Hence, the shunt motors are suitable where the speed has to remain approximately constant over a wide range of the load, that is A characteristic. So, in series motor the flux is increases as the in proportional to the current and then less rapidly owing to magnetic saturation. So, this RA in the above expression now include the resistance of field winding, and the speed is roughly inversely proportional to the current as indicated by curve B, this characteristic. And it will be seen that if the load falls to a very small value, then the speed may become dangerously high as it going up, and a series motor should therefore not to be employed when there is any such risk of very low load or light load operating condition of the motor. So, for instance, it should never be belt coupled to its load except in very small machines such as vacuum cleaner. So, since the compound motors has a combination of shunt and series excitations, its characteristic like a C is intermediate between these two shunt and series motors. So, the exact shape depending upon the value of shunt and series ampere turns. So, now coming to the typically torque speed characteristic of these DC motors. So, here we can call it like it was shown that for a given motor torque is proportional to armature current into flux per pole, and now you have a armature current versus torque for different motors like A is for shunt, and we already talk about C is for series and B is for compound. So, since the flux in shunt motor is practically independent of armature current, so torque of shunt motor is proportional to armature current. So, M is proportional to IA since flux is almost constant. So, in a series motor the flux is approximately proportional to the current to up to full load. So, the torque of a series motor is proportional to armature current is approximately, and that is M proportional to IA square. So, above the full load magnetic saturation becomes more marked and the torque does not increase so rapidly. So, curves A, B, C in figure shows that relative shapes of torque for shunt, series and compound motor having the same full load correct at OQ with the same full load armature current of OP, and with the exact shape of curve C depends upon the relative value of the shunt and series at full load. From figure it is evident that for a given current below the full load value, the shunt motor exerts a largest torque, but a given current above that value, the series motor exerts the largest torque. So, the maximum permissible current at starting is usually about 1.5 times the full load current. So, consequently, a large starting torque is required such for hoist, cranes, electric crane, etc. So, series motor is considered to be the most suitable motor for such application. Now, coming to the speed control of DC motor, the typically coming with the separately excited shunt motor whose field is supplied by a separate source, as you can see in this case with the constant voltage power supply. So, we have armature circuit here and we have a field circuit. So, it is a equivalent circuit of separately excited DC motor. So, these are armature resistance, here a field resistance, then the typical inductance of the field winding for an additional resistance we put it. Typically we can take total resistance of course into the circuit for the calculation. So, here IF equal to V upon RF and VT equal to EA. Here EA plus IRA and where IL equal to IA, because this is same current in case of separately excited motor. So, DC shunt motor is a motor whose field gets its power directly across the armature terminal of the motor. So, here it is you can call it IF equal to VT upon RF and VT equal to A plus IA, and IL that is line current drawn from supply is IA plus IF, that is divided into 2. So, that is typically the difference in separately excited and DC shunt motor. So, now terminal characteristic of DC shunt motor, a terminal characteristic of a machine is a plot of machine output quantity versus each other. So, for a motor the output quantity are shaft torque and speed. So, the terminal characteristic of a motor is a plot of its output torque versus speed. So, the KVL equation for a shunt motor is V T equal to E A plus I R A. So, terminal characteristic of DC shunt motor is induced voltage E A equal to K phi omega m. So, V T equal to K phi omega m plus I R A. So, T load equal to K phi I A. So, current I A can be expressed as I A equal to T in upon K phi, and we can call it combining these equations V T equal to K phi omega m plus T upon K phi into R A, and finally solving for the speed, this omega m will be V T upon K phi minus R A upon K phi square into T. This equation is just a straight line with the negative slope. So, this is the torque speed. The resulting torque speed characteristic of DC shunt motor is shown here, that is the speed. This is the torque and this is the speed. So, speed reduces slightly with the increased torque. So, torque because of the second term, but however, that term is quite small compared to the your no load speed, which is V upon K phi. So, torque speed characteristic of shunt motor or separately excited DC motor with compensating winding to eliminate the armature reaction. So, in order for the speed of the motor to vary linearly with torque, the other terms in this equation must be constant as the load changes, and the terminal voltage supplied by the DC power source is assumed to be constant. If it is not constant, then the voltage variation will affect the shape of the torque speed characteristic, and if a motor has armature reaction, then it is correct load. As its load increases, the field weakening effect reduces its flux. The effect of reduction in flux is to increase the motor speed at any given load over the speed it will run at without armature reaction, and that is the characteristic how this torque speed characteristic is modified with no armature reaction and with armature reaction. That is the practical aspect. Of course, these motors have armature reaction effect, like the torque speed characteristic of DC with the armature reaction present. So, now question is how can the speed of a shunt motor can be controlled. So, we can control by adjusting the field resistance and thus the flux, and adjusting the terminal voltage applied to the armature circuit and inserting a resistance in series with the armature circuit. So, now changing the field resistance, if the field resistor of DC motor is changed, assuming that the field resistor increases and observe the response. So, if the field resistance increases, then the field current decreases, that is I F equal to V T upon R F increases, R F increases and the field current decreases, thus the flux decreases with it, and this a decrease in the flux causes stress in decrease in the internal generated voltage, and which causes a large increase in the armature current. I increases as the E decreases in this equation. So, to summarize the cause and effect behavior involved in this method of speed control. So, increasing R F causes I F to typically decrease, and that is V T upon, as R F increases. So, V T upon R F decreases, and decreasing I F decreases the phi, and decreasing phi lowers the E A, and decreasing E A increases the armature current, and then increasing I F increases the torque with increasing the dominant over the flux, and increasing torque makes the T more and the speed increases, increasing speed increases E A again, and increase E A I decreases I A, and decreasing I A T until T developed by the motor is equal to load torque at the higher speed omega. So, this causes, like you can see the effect of field resistance speed control of a DC shunt motor characteristic over the normal characteristic. So, this is normal, and when we insert additional resistance, because RF2 is 2, the speed characteristic gets shifted up, I mean typically because of the decrease in field current, and that causes to increase even the no load speed as well as the speed at all other load torque or developed torque. And this is virtually, you can call it, if we really increase further high speed up to certain, it decreases, but after that the effect for typically you can call it, I mean for the large torque the speed decreases here, as if this condition is certainly correspond to very large torque on the shaft of the motor. So, effect of the field resistance speed control of this characteristic over the entire range from no load to the installed condition. Now, coming to the speed control of this DC motor by changing the armature voltage. So, this speed control involves the voltage applied to the typically the field and armature voltage of the shunt motor separately excited DC motor. So, here we are going to apply the variable voltage with the controller and field is separate. So, now the speed control for different here also if you change the armature voltage, when you increase the armature voltage then you will get higher, but you cannot increase the armature voltage more than rated. So, you have to decrease only the armature voltage. So, whole characteristic shift to down this torque is characteristic because even the voltage you have decreased, so no load speed also decreases. So, effect of armature voltage speed control torque speed characteristic and changing the armature voltage to summarize the cause and effect behavior in this method of speed control. An increase in VA increases IA and increasing IA increases torque and increasing IA increases torque that becomes more than low torque and increasing omega m. So, now it increases the omega m, increases the EA decreases and decreasing IA decreases until the developed torque becomes equal to low torque at higher speed, and that is the effect of how you are changing or decreasing the voltage. So, now inserting resistance in the series with the armature circuit. If resistance is inserted in series with the armature circuit, the effect is to drastically increase the slope of motor torque speed characteristic, making it operate more slowly if loaded, and it can be seen from the equation that omega m equal to V T upon K phi, that R upon K phi square into T induced, and that RA you are going to increase, it means second term is going to increase more. And this is the effect like when you are increasing more and more resistance, as you can see, no load speed will the same, but the speed at increasing load will decrease of this, but this method of course used for very low rating motor, otherwise you have to dissipate a lot of power or energy into the this sectional resistance which you are keeping here. So, efficiency goes down. So, very low speed, very low rating motors only this is afforded, otherwise the voltage control, armature voltage control below base speed and field control above base speed are considered to be the best method to cover a overall wide speed range. Now, for a DC series motor, series motor is a DC motor whose field winding consists of relatively few turns connected in series with the armature, because same current flows into the field winding. So, you have to keep a thick conductor for field winding and resistance is supposed to be small. So, that losses are not there in the whole armature circuit. So, here armature current and series field current equal to the line current, and now we can say V T equal to EA plus IA in parenthesis RA plus RS. So, here the Kirchhoff's voltage law equation of this motor V T equal to EA plus IA with RA plus RS, and the basic behavior of series DC motor is due to the fact that the flux is directly proportional to the armature current at least until the saturation is reached, and as the load on the motor increases, its flux increases too. So, well, assuming the linear magnetization characteristic in the sense phi is proportional to C into IA, where C is the constant of proportionality, then Kirchhoff's voltage law we can say V comma equal to EA plus IA RA plus RS. So, induced torque or developed torque by the machine is T induced equal to K phi IA, and that is Kc into IA square, and armature current can be expressed as IA under root T induced divided by Kc. So, here we can call it EA equal to K phi omega m, substituting into the equation V gamma equal to EA plus IA RA RS. So, we can call it V T equal to K phi omega m under root K T induced upon Kc in bracket RA plus RS. So, if flux can be eliminated from this expression, it will directly relate to the torque of the motor to the speed. So, to eliminate the flux from, we can say IA is phi upon C. So, we can say here the induced torque equation can be K phi into T equal to K upon C phi square. So, there the flux in the motor can be written phi equal to C upon K into T under root T induced. So, substituting this, we can say V T equal to K phi omega under root T induced K by Kc RA plus RS, and then putting this value of the typically of flux K T under root C upon K under root T induced into omega plus under root T into Kc RA plus RS, and we can say now under root Kc under root T induced into omega equal to V T minus RA plus RS under root Kc into under root K induced, and resulting torque speed relation can be omega upon V gamma upon under root Kc into T induct minus Ra plus Rs into divided by Kc. So, the torque characteristic from this equation can be plotted. You can see this is the speed corresponding to full load torque, that is the speed, and if you increase the load, the speed decreases. If you decrease the load, speed increases. So, this is what we call it the torque characteristic of DC series motor, how we obtain. So, of course, getting the speed control of DC series motor, unlike the DC shunt motor, there is only one efficient way to change the speed of DC motor, that is the method to change the terminal voltage of the motor. And if terminal voltage increase, the first term of equation here with the voltage is increased, resulting in a higher speed and or at given torque. So, the speed of a DC series motor can also be controlled by insertion of a series resistor into motor circuit, but this technique is very wasteful of power and used only for intermittent period during the start of the sum motor. Now, coming the speed control by thyristor system of speed control, that is solid state control. So, the simplest method is here, that we are giving, normally we have AC supply. So, what we do, we use the diode rectifier to excite the field winding by DC, and armature winding, of course, we use the thyristor which control the voltage in the output, and thyristor is off, freewheeling diode allow the circulating of the current in this armature circuit, because the inductance of armature is already very large. So, current will remain continuous in that case, but you can vary the voltage, average voltage across the armature, which really will control the speed from 0 to the rated, because you cannot apply the more than rated voltage across the armature winding. So, field winding F is separately excited with the bridge connected, diode bridge connected with the rectifier J, and armature is supplied by a thyristor T, and gate G of the thyristor is connected to firing circuit, who supply a current pulse once every cycle. So, arrangement of this firing circuit is not shown, as it is 2 volt for inclusion of in this diagram. So, in figure R and all represent the resistance and inductance respectively of armature winding and external inductor that may be inserted to increase the inductance of the circuit. A diode is connected across the armature and the inductor to the, you can call it how the waveform. So, this is typically the speed, this is the supply voltage, and this is your, you can call it the current, typically kind of pulse. So, you can call sine wave in figure represent the supply voltage, AC voltage, and where the line Mn represent the EMF generated by the rotation of the armature, and the value of ER is proportional to the speed, which in turn varies with the armature current line. So, thus when the current exceeds the armature value, average value, the current, the armature accelerate, and then the deaccelerate, and the armature falls below the average value, and the speed fluctuations of course indicated here, aggregated, illustrated is more effective. So, that is the typical waveform of this motor. So, suppose a current pulse is to be applied to the gate pulse at extent of P. Here you will find the resulting current through the thyristor and the armature grows at rate depending upon the difference between the applied voltage and the rotational EMF ER, and upon the ratio of LR of the circuit. So, you will get here V equal to ER plus IR plus LdI by dt. So, I becomes V minus ER in minus LdI by dt into R, and when the thyristor is conducting, the potential difference across the armature and inductor, and therefore, across diode varies as shown in the full line waveform figure, and at the instant q where E equal to E. So, I equal to minus L upon R, that is d I by dt. So, the current now decreasing, so that d I upon dt is negative. So, hence the current is still positive, and therefore, the continue to exert a driving torque of the armature. As you can see here, this is the typically the current flowing here. So, instant supply voltage reversing in direction, and reverse current from the supply flows through D, supplying the making the cathode of the thyristor positive relative to anode, and consequently, the current I1 through the thyristor falls to 0 as indicated here, and the dotted line of figure typically shown here, that is the virtually the armature current in conducting state. So, current now confined to the closed circuit formed by the armature and diode, and since potential difference across die is practically 0. So, equation is I equal to V minus ER minus LdI by dt. R now can be written as I equal to minus ER minus LdI by dt into R. So, LdI by dt is to exceed ER, since the value of dIpt is negative and the direction of current is unaltered, and hence the current is still continue to exert a driving torque on the armature. The energy supplied to the load being recovered partly from the stored in the inductance of the circuit while the current was growing, and partly from the stored as kinetic energy in the motor as loading during the acceleration. So, the dotted curve typically here the current I2 through the diode, and the latter is often referred to a freewheeling diode since it carries the current when thyristor is to conduct. So, later the instant of firing the thyristor, the smaller is the average voltage applied to the armature and lower the speed in order to that the motor may make the same average current from the supply to enable it to maintain the same load torque. So, thus the speed of motor can be controlled over a wide range. An increase of motor torque causes the speed to fall, thereby allowing a large current pulse to flow during the conducting period, and the fluctuation of current can be reduced by following: using 2 thyristors to give full wave rectification when supply is a single phase, using 3 or 6 thyristors when supply is 3 phase. An important application of thyristor is in the speed control of series motor in a battery driven vehicle. So, the principle of operation is that pulses of battery voltage are now applied to the motor, and the average value of the voltage across the motor is controlled by varying the ratio of on off duration of the pulses, and this on pulse is T1 and off pulse is T2. So, average voltage equal to battery voltage T1 upon T plus T2. So, that is the method of speed control. Now, coming to the solved numerical problem, starting the first problem, a DC generator carries 600 conductor on its armature with lap connections. So, generator has 8 poles with 0.06 Weber useful flux. So, what will be the induced EMF in terminal rotated at 1000 rpm, also determine the speed at which it should driven to induce same voltage with wave connection. So, here P equal to 8, phi equal to 0.06 Weber, N equal to 1000 rpm, Z equal to 600, A equal to P 800 for lap winding. So, induced EMF is equal to P phi Z upon 60 A. So, putting the value it comes 600 volt. Now, for wave connected parallel path is 2. So, now N dash will be Eg into 60 upon P phi Z, putting the value it becomes 250 rpm. Now, having a solve example 2, a wound armature of an 8 pole generator has 51 slot, each slot contains 60 conductor, and the voltage required to be generated 300. What will be the wave speed of the prime mover if flux per pole is 0.05 Weber? If the armature is rewound as a lap wound machine and run by the same prime mover, what will be the generated voltage? So, where P equal to 8, phi equal to 0.5 Weber, and number of slots 15, conductor of slot 16. So, Z equal to 15 into 16, that is 816. When armature is wave wound, A equal to 2 and is equal to 300. So, we can putting the value here, we will get typically N from here is 110.3 rpm. So, when machine is rewound for lap winding, A equal to P equal to 8, then this is equal to 75. And now, coming to solve example 3, a 4 pole wave wound DC generator has a 51 slot on its armature, and each slot has a 24 conductor. The flux per pole is 0.01 Weber. At what speed must the armature rotate to give the induced voltage of 220 volt? What should be the induced EMF if the winding is lap connected and armature rotates at same speed? So, phi equal to 0.01 Weber, Z equal to 51 24, 1224 equal to 220, P equal to 4, A equal to 2 for wave winding. So, putting the value we will get induced EMF, and here from this we can get N equal to 539.21 and Eg comes from putting the value in case of, so it get 110 volt. Now, coming to for example 4, a 4 pole motor is fed from 400 volt and takes a armature current of 50 ampere. The resistance of armature circuit is 0.28 ohm. The armature winding is wave connected with the 888 conductors, and the usual flux per pole is 0.023 Weber. Calculate the speed. So, from expression we have 440 in generated induced EMF plus 50 into 0.28, that is the, you can call it the IRA drop. So, generated EMF is 440 minus 14, that is 426, and substituting the value in the EMF equation of this 426. So, we get NR equal to 626 rpm. Now, coming example 5, a motor runs at 900 rpm of a 460 volt supply. Calculate the approximate speed when the machine is connected across the 200 volt supply. Assume the new flux to be 0.7 of the original flux, and here the solution phi is the original flux, and from the expression we can NR is proportional to V upon phi. So, putting the value here we can get K phi, that is 0.511, and now new speed is new voltage divided by K into original flux into 0.7. So, NR comes from putting the value, it comes 559 rpm. Now, coming to example 6, a DC motor takes a armature current of 110 ampere at 480 volt, and the resistance of armature circuit is 0.2 ohm. The machine have a 6 poles and the armature is lap connected with 864 conductor. the flux per pole is 0.05 Weber, calculate the speed, the gross torque developed by the armature, and solution generated induced EMF 480 minus 110 into 0.2, that is 458. So, the armature winding is lap connected, so C equal to 6, so E equal to 2 Z upon C into NRP upon 60 into 5. So, putting the value, we get NR equal to 636 RPM, and mechanical power developed by the armature is your E into IA, that becomes 110 into 458, that is 50,380 watt, and substituting the expression, we have here 2 pi m into n upon 60 equal to 50,380, that then the m becomes 756 Newton meter. So, alternatively using the expression, we can find out m equal to 0.318 into I upon C into Z P 5 Newton, and putting the value, we get same 756 Newton meter. Now, coming example 7, the torque required for to drive a DC generator at 15 RPS is 2 kilonewton meter. The core friction and windage losses in the machine are 8 kilowatt. Calculate the power generated by the armature winding. So, driving torque is 2 K Nm, that is 2000 Newton meter, and from expression of power required to drive the generator is 2 phi into m into RPS, that is I am multiplying this. So, 15, that come 188,400 and 188.4 kilowatt. So, since core friction voltage are 8 kilowatt, so power generated by armature is 188.4 minus 8, that is 180.4 kilowatt. Now, coming example 8 is DC series motor runs at 600 RPM when taking a 110 ampere from the 250 volt supply. So, resistance of armature circuit is 0.12 ohm, and that of series winding is 0.03 ohm. The usual flux per pole is 100 for 120 ampere is 0.024 Weber, and that of 50 ampere is 0.0155 Weber. Calculate the speed when the current has fallen to 50 ampere. So, the total resistance of the armature and series winding is 0.12 plus 0.03, that comes 0.15 ohm. So, therefore, EMF generated at 110 ampere is 250 into minus 110 into 0.15, that is 232 volt. Now, generator EMF is a constant into speed into flux. So, hence with 120 ampere 232 into K into 600 into 0.024, K comes to 16.11. So, with 50 ampere generator induced 250 minus 50 into 0.15, that becomes 241.5 volt. And now, new induced EMF is K into new speed into new flux. So, that is 240.5 equal to 14.82 into new speed into 0.0155. So, speed for 50 ampere is 971 RPM. Now, coming to example 9, a DC shunt motor is running at 626 RPM when taking an armature current of 50 ampere from a 440 volt supply. The armature circuit has a resistance of 0.28 ohm. If the flux is suddenly reduced by 5%, A, the maximum value at to which the current increases momently, and the ratio is the corresponding torque to the initial torque, and ultimate steady state value of the armature current, assuming the torque due to load to remain unaltered. So, the first is initial EMF generated is 450 minus 50 into 0.28, that is 426 volt. Immediately after the flux is due to 5%, therefore, the speed has begun to increase. So, EMF generated is 426 into 0.95, that is 404.7. So, therefore, corresponding voltage drop due to the armature resistance is 440 minus 404.7, that is 35.3 volt, and corresponding armature current will be that 35.3 divided by 0.28, that is 126 ampere. So, the torque of the machine armature current multiply the flux. So, now new torque divided by initial torque into new current divided by initial current to new flux upon initial. So, putting the value, it comes typically 2.394. So, hence the sudden reduction of 5% the flux is accompanied by a more than two-fold increase of torque. This is the reason why the motor accelerated, and after the speed and current have attained steady state value, the torque will have to decrease to the original value. So, the current now new current in new flux equal to original current of new flux. So, new armature current is 1 upon 0.5, that is 52.6 ampere. Now, coming to example 10, a 12 kilowatt 6 volt DC generator develops an induced EMF of 240 volt at 1500 RPM. The armature has a lap connected winding. The average flux density over the pole pitch is 1 Tesla. The length and the diameter of the armature is 30 centimeter and 30 centimeter and 25 centimeter respectively. Calculate the flux per pole, total number of active armature conductor, power generator in the armature, and torque developed when machine is developing 50 ampere at load. So, P given here for solution, P equal to 6, V equal to 240, N equal to 1500 RPM, A equal to P equal to 6 for lap connected winding, and B equal to 1 Tesla, D equal to 0.25 meter, L equal to 0.3 meter, and I equal to IL equal to 50. So, now flux per pole is B pi d upon P into L, putting the value it comes 0.0393 Weber, and now E g equal to P phi Z upon 68. So, putting the value here Z comes 244. Now, power developed in the armature P is equal to E g into I a, that is 240 into 50, that is 12 kilowatt, and the torque developed is P g upon omega. So, putting a value P g upon 2 pi upon 60. So, 12 P g 12,000 into 60 by 2 pi into 1500. So, it comes 76.4 Newton meter. Now, coming example 11, a DC generator is connected to a 220 volt DC mains. The current delivered by the generator to the mains is 100 ampere. The armature resistance is 0.1 ohm. The generator is driven at a speed of 500 rpm. To calculate the induced EMF, the electromagnetic torque, the mechanical power input to the armature, neglecting the iron winding and friction losses, and electrical power output from the armature and armature copper loss. So, now coming to solution, the induced EMF is equal to V plus IARA for generator, and this is 220 plus 0.1 into 100, that is 230 volt. Using the relation omega t equal to E g I a, the electromagnetic torque is E g I upon omega, and putting the value it comes 439.27 Newton meter. Neglecting the iron winding and friction losses, so input the armature is omega t, that is equal to E g into I a. From there you can put the value 2 pi into 160 equal to this comes 23 kilowatt. The electrical power output is V I a, that is 220 to 100, that is 22 kilowatt, and armature losses I square R a 100 square into 0.1, that is 1000 watt. So, now these are the unsolved problems which you can solve in the similar manner as we discussed the examples, and these are the some of the references from which we developed this lecture, and thank you very much.